In this video, I'd like to show you a way that you can graph polar equations. Instead of calling it a cool trick, maybe it would be better titled as a helpful approach, because this technique won't work on every single polar equation you ever come across, but it will help you better understand how graphs of polar equations work, and it will help you graph a whole mess of polar equations that you'll come across throughout the rest of the video. Before even starting, I could summarize the helpful approach very simply. Imagine you had a set of points that you wanted to connect, and these were polar points, and you knew that A came before B, and B came before C, and C came before D. This approach is just connect the points not linearly like this, but rather with a swirling motion, and it should be a counterclockwise swirl. There we go. That's how you would connect the points. That's the general strategy. So let's see it with a few particular examples. So the first example we have here is a rather complicated example. So I'll need the help of Desmos. This is the example r equals 2 sine of 2 theta plus sine of 3 theta. And I want to make a polar graph of this equation. So the reason I reached out to Desmos for help is what I'm going to start with in order for this technique to work is a nice graph of the equation as if r were y and theta were x. So this is a r versus theta graph. It's not converting the equation to rectangular. It's simply saying, what would this look like if the equation was y equals 2 sine of 2x plus sine of 3x, and we weren't trying to graph it all swirly, but instead plot the way the radius changes up and down as theta increases left to right. So what I'll do here on my graph is I'll identify some really, really important points. And this is what you'll do as well for your technique. Important points will consist of whatever point it begins at, any maximum point, anytime it reaches the x-axis, any minimum point, and I'll continue like that all the way across. Now notice I'm actually not going to label the points along the x-axis with a letter, and the reason for that is any point along the x-axis is going to represent the pole. So I don't want a whole bunch of different letters cluttering up the pole. I'll just label it with letter A, and anytime I visit the pole, I'll go back to point A. That'll be all those x's will be point A again. Okay, so in plotting point B, I see it has an angle of 36 degrees and a radius of about 2.4. So 36 degrees, 2.4 might be right about here, so I'll plot point B. And then I'll plot point C. Now point C, you want to be a little careful because you notice that with point C, the radius is less than 0. It's about -1.5. So you don't want to plot it at 108 degrees measured from the positive x-axis. You want to do 108 degrees measured from the negative x-axis. So it would kind of look like this. If I went to -1.5, that would be about here on the negative x-axis, and then I'd have to trace out from there 108 degrees, which would put me right about here. So here's about where point C is. Next, I'll plot point D, which has the same radius as C, except it's positive, and it's at 252 degrees, so that might be right about here. Here's point D. And last, I'll plot point E. This is another negative radius, so it's 324 degrees measured from the negative x-axis. So if you're thinking that's going to be way around here in quadrant 2, you would be right. So point D is right about point E is right about there. Okay, now it's time for that game of connect the dots that I mentioned. So let's see, I'll just connect it maybe in green so you can see it real nicely. I'll start at point A, and I'll use that counterclockwise swirling motion to get out to point B. And after I visit B, I see that I need to go back to the pole, so I'll go back to point A. And then I move out to point C, which is down here, still continuing the counterclockwise swirl, and back to the pole again. And then I notice that I go out to point D and back to the pole again. And lastly, out to point E and back to the pole one last time. So I made these nice little set of wings. And the big idea was just consider r versus theta as if they were rectangular and play a game of connect the dots. Let's look at one other complex example and then a simple example. In this example, I'll take a look at the graph of r equals 2 sine squared of theta minus 2 sine of theta. So once again, I'll use Desmos here to help me out. This is a graph of r versus theta as if r were on the y-axis and theta were spread out on the x-axis. You can see some important points here. It begins at the origin again, and it hits this minimum. I'll call this point B, and then it visits the origin again, and another minimum point C, and then it visits the origin again. And then this point right out here, D, that's a very extreme point. Definitely want to mark that. And then I can see that it visits the origin one last time. I won't mark this point down here because that's greater than 360 degrees, and the period of this sinusoid happens to be 360 degrees, so it just repeats itself. Well, okay, so if I start with point A would go right here at the pole, and then point B, I see I've got a negative radius again. So that would be 30 degrees and negative 1/2 with quadrant 3 because it's measured from the negative x-axis. So there's point B. Point C would be another negative radius, 150 degrees measured from the negative x-axis. So that would be over here. And okay, let's just actually play a quick game of connect the dots with those points. So it would go from A out to B, back to A because it goes back to the pole, out to C, back to A. Okay, so far so good. Made a little infinity-like symbol. And this is the really, I guess, important part of the graph where it zooms out to point D. And point D is 270 degrees with a radius of 4, so that's way down here. Here's point D way down here. So for my graph to zoom way out, that means my radius is going to get really large really fast. So I'm still moving in this counterclockwise motion, but I want the radius to get really large really fast, and then it just does the opposite, coming back to the pole. So it swings back around, and you make this little green tomato looking thing. Okay, I promised a simple example, so let's look at one simple example. So for our simple example, let's look at, let's say r equals 2 sine of theta. So you might remember equations of this form. You can show by converting to rectangular that this is going to create the equation of a circle. Nice little exercise if you are forgetting how to do that, maybe multiplying both sides by r and completing the square. But this video is not about converting it to rectangular. It's just about thinking about its graph as if theta were on the x-axis and the radius were on the y-axis, and graphing this as just a very simple sinusoid. So 2 sine theta, that starts at the midline, goes to its maximum. Its maximum is going to be 2 instead of 1 because amplitude is 2. Comes back to its midline, down to its minimum at negative 2, and then back to its midline. So here is our graph of 2 sine theta. All right, and the important points that you can see on there, of course, are at the origin, 0, 0. Point B up here, this has coordinates pi over 2, comma 2. Back to the origin, I'll call that C. This point down here, D, a minimum, is an important point to graph. In fact, any point, min, max, or midline would be a very important point to graph. And then lastly, point E, which is 2 pi, comma 0. Okay, so as I plot these on my polar grid, you can see why it's making the equation of a circle. I start at 0, 0. Radius is 0, angle of 0. That's point A. And then point B is an angle of 90 degrees and a radius of 2. That's up here. And the technique says that I should connect A to B in this counterclockwise swirling motion. So that would look like that. And next, B goes back to the pole. So point C would be back here, in the same spot A was. Now, what about D? D has a negative radius and an angle of 3 pi over 2. Point D would not be down here. That would be a positive radius with an angle of 3 pi over 2. Point D is in the exact same spot as point B. And then point E is in the exact same spot as point A and C. So what that means is we just swirl around the circle a second time. And that's how you can quickly graph a relatively simple polar equation. In addition to circles, you'll be able to graph things like cardioids and limacons and roses using this technique, because all of them have equations that can be graphed like this very quickly. Okay, so just to put everything together here, literally, if I were to take all the graphs that we made today and put them in the same graph, let's see what we get. There we go. So what we have is, we had a graph r equals 2 sine 2 theta plus sine 3 theta, and that made those little wings. And then next we had this graph r equals 2 sine squared theta minus 2 sine theta, and that made that green tomato, which is now a blue tomato. And there we have a little head for the fairy. That is the graph of r equals 2 sine theta. Oh, but I shaded it in, so all I actually used there was a less than or equal to sign to shade in the fairy's head. Hope you liked the video. Hope it helps you graph the polar equations you come across in the rest of the exploration.